Hello, multivariable calculus students. This is Mr. Johnson, and this is the last video for section 10.3. You just saw the first four examples on velocity and acceleration and position, and then the last video that you saw was on the components of acceleration, and I went in pretty in depth as to where the formulas come from. Now, keep in mind that I often will write these with relationship to the velocity and the acceleration. So this is how I often will write them. And the reason for this is that we're talking here specifically about the components of acceleration, and so therefore I'm thinking about it in terms of position, velocity, and acceleration. So anyway, you can look at that video for that information. In the video, I do mention that that the vector b is not associated with the acceleration vector. The acceleration vector, no matter how the object moves in space, is always in the oscillating plane, which that oscillating plane is made up of t and then n. And so we don't have to worry about that vector b because that's sort of coming out of the page at you or going into the page. Okay, let's go through a couple examples on the next page. All right, we're just going to practice calculating the tangent and the normal component of acceleration. So the first thing we're going to do is find the velocity, so the derivative of our vector function, which is going to be 2t and then 2t and 3t squared. And then we'll also do the acceleration, which is 2, 2, and then 6t. Now we're going to calculate both the dot product of these two and the cross product of these two based on our formulas. So let's do the dot product first. Here we get 2 times 2t, so we get 4t, and then plus 4t again, and then we have 18t to the third. We can simplify this to be 8t plus 18t cubed. So there's our dot product. We'll use that for the tangent component of acceleration. We also need the cross product between the two. So I'll set this one up. I'll pause and then set this one up. Okay, so here's our cross product. Now you're going to want to do the magnitude of this. And so remember, I've mentioned this before, but one thing that we can do that saves us a lot of time is that we can factor out the greatest factor. And when you take the magnitude now of v crossed with a, the magnitude of 6t squared is of course itself, because you would just take the square root of it squared. And then the magnitude of 1, negative 1, 0 will be the square root of 2. So that's a much easier way to do the magnitude. We also need the magnitude of velocity. That will be the division for each of these elements. And so the magnitude of velocity is going to be the square root of 4t squared plus 4t squared plus 9t to the fourth. And we could simplify that down to 8t squared plus 9t to the fourth, and we could actually factor out a t squared and take the square root. So we could get, for this one, t times 8 plus 9t squared. Okay, I think we have all the different elements we need. So for the tangent component of acceleration, that's going to be v dotted with a divided by the magnitude of v. And so we're just going to substitute in all of our different pieces here. We have 8t plus 18t cubed divided by the magnitude of v, which is t times 8 plus 9t squared. And we could divide by t here, which would give us 8 plus 18t squared divided by the square root of 8 plus 9t squared. So that's one of our components. And then our second component, the normal component of acceleration, we're going to do the cross product, which is going to be 6t squared times square root of 2. And we're dividing by the same thing, the magnitude of v. And here we could cancel a t as well. So we have 6t times the square root of 2 divided by the square root of 8 plus 9t squared. Okay, let's try our next example, example 6. So we're doing the same thing here. If you wanted to pause it, for example, try this one and then you could check back in, that'd be totally fine. We're going to do the same approach. We're going to take the velocity first. So negative sine t and then cosine t and 1, and then we're going to do the acceleration. That will be negative cosine t, and then negative sine t and 0. And then the next step is to do the dot product between the two. So when we do our dot product, what we get is positive sine of t, cosine of t, and then plus, and then it's going to be a negative. So let's just make that a minus sine t, cosine t, and then of course 0. And that gives us a total of 0. So the dot product is 0. That one's pretty easy. And then we're going to do the cross product. And I'll set this one up. I'll pause and set this one up. Okay, here's our cross product, and then if you want to simplify, you get sine of t, negative cosine t, and 1. And then of course we'll do the magnitude of this cross product, which is simply square root of 2. And let's see, the last thing we need is the magnitude of v, and that is also the square root of 2, and then I think we're all set here. So let's do the tangent component, which remember is v dotted with a divided by the magnitude of v. And so we end up getting 0 divided by the square root of 2, which is of course 0. And then we have the normal component, which is the magnitude of the cross product, divided by the magnitude of v. And that will be the square root of 2 divided by the square root of 2, and that gives us 1. Okay, let's go on to the next page. All right, here we have just a couple review problems, and it's really good, especially at this point in the year where we're working through all of this stuff, not to forget some of the parts that we did in Chapter 9, because we do obviously connect these ideas together. And so in the first review problem, we're going to look at the point of intersection of the plane and the line. And this line in parametric form is x equals 1 plus 3t, y equals 0 plus negative 1t, so negative t, and then z would be negative 2 plus 2t. And what I'll do is substitute each of those values into the equation for a plane. So for instance, I'm going to substitute in 1 plus 3t for x, minus 2 times I'm going to substitute negative t for y, and then plus 3 times, and I'm going to substitute negative 2 plus 2t for z, and it's all equal to 11. And so we'll just work on simplifying this really quickly. So we have all of our elements, and we can combine like terms and ultimately solve for t. So we get a total of, let's see, that's going to give us 11t, and if we move everything else over, we get 16. So t is equal to 16 over 11. And from here, we want to substitute that back into our x, y, and z so we can find our point at which these intersect. So we have for x1 plus 3 times 16 over 11, that's going to be 59 over 11. And then y will be negative 16 over 11. And z will be negative 2 plus 2 times 16 over 11. And that gives us just 10 over 11. And so our point of intersection here is going to be 59 over 11, negative 16 over 11, and then 10 over 11. All right, let's go to our last example, example 8. This review is from way back in the beginning of Chapter 9, where we talked about the area of a parallelogram spanned by two vectors. So first of all, let's go ahead and graph this out. I'm going to graph it. I'm going to pause and then I'll graph it. All right, so here's my best sketch for you. So that's the parallelogram. The red vector is 2, 1, 0, and then the blue one is negative 3, 1, 0. And remember, they have to have the same initial point. And if we were to take the cross product between these two, that gives us the area of this parallelogram. So I will pause and set this one up as well. All right, it's a pretty easy cross product to perform. And remember, we're going to take the magnitude of this in order to get the area of that parallelogram. And that's, of course, 5. So that does it for section 10.4. Thank you.